Our voice.
Yeah.
Sir, మీ screen sharing.
మేడం చిన్న ప్రాబ్లం సేమ్ ఉన్నలాగానే వచ్చేస్తుంది. మేడం
Hello? Sir, our voice is not audible to you. Both of us, our voice is not audible to you. Your voice is audible to us. Hello? Okay, you have told him to start. Okay.
Sir, may I start the class now?
So start, sir.
Okay. So welcome back to our YouTube channel, TREAS. So previous class we have discussed about the electrochemistry. Some of the topics were completed. Now today's class we will discuss about the Kohlras Law as well as its application, and the second one, Faraday's Law. So these two topics will be discussed in this class. So see this one. So what is the reason to invent that Kohlras Law is? Before that we will discuss about the variation of this one. See this one. Yeah, variation of conductivity and molar conductivity with dilution. That means what is the effect of the dilution on the conductivity as well as molar conductivity, we will discuss first of all. So what will be happen? Conductivity will be decrease in the concentration. Okay, yeah, so that is the direct relation is there between the concentration as well as conductivity. That means dilution as well as whatever the conductivity as well as concentration. Why? By decreasing the concentration, conductivity is decreasing. What is the reason? Because the number of ions per its units volume is decreases. Okay, so number of ions is decreasing for the unit volume. That's why what will be happen? Conductivity will be decreases. Why? Because conductivity depends upon the number of ions. Okay, so here number of ions decreases. That's why conductivity decreases on dilution. Similarly, what is the effect of the molar concentration? By decreasing the concentration. So by decreasing the concentration, so what will be happen? Molar conductivity will be increases. Okay. Why? Because here the total volume V of the solution will be increases. So by increasing the electrolytic solutions, what will be happen? Molar conductivity of the solution will be increases. So indirect relation between the molar conductivity and direct relation between the conductivity. See this one. So next we will discuss see this one. So molar conductivity always increases with the decrease in the concentration of both for the weak electrolyte as well as strong electrolyte. For example, we are taking here acetic acid is a weak electrolyte. All weak acids as well as weak bases comes under the, what is that one, weak electrolytes. All strong acids as well as strong bases comes under the strong electrolytes. Whatever the electrolyte, whether it is a weak or strong. So what will be happen? By decrease in the concentration, molar conductivity will be increases. Indirect relationship between these two. So yeah, so here one graph is there. So see this graph. By plotting a graph between the molar conductivity lambda m. So here Siemens centimeter square mole inverse, these are the units, and here C, root C is a concentration. By plotting a graph between the molar conductivity as well as concentration, what is happening? You have to observe here. Okay, so this is KCl. KCl is a strong electrolyte, and CH3COOH. CH3COOH is a weak electrolyte. This is a weak acid. That's why this is a weak electrolyte. So by plotting a graph between the lambda m, molar conductivity, as well as concentration, what is happening? When concentration approaches to zero, here concentration here 0, 0.0, 0, 0.1, 0.2, 0.3, 0.4, 0.5, like that. This is a one of the axis. This is concentration, and this is another axis. This is molar conductivity. So by increasing the molar conductivity here, concentration, what is happening? This is decreasing. Okay, yeah, indirect relationship is there. When concentration approaches to zero here, 0.4, 0.3, 0.2, 0.1, 0 approaches to zero, the molar conductivity is known as limiting molar conductivity here. So when approaches to zero, this is called as molar limiting molar conductivity. Okay, what is the symbol? It can be represented lambda naught m. Here naught indicates the limiting. Okay, lambda naught m, limiting molar conductivity. So here, what this picture indicates the limiting molar conductivity of the strong electrolytes as well as weak electrolytes. Okay, by plotting a graph, by extrapolation of the graph KCl. So here we are taking 0.1, 0.2, 0.3, 0.4 molar conductivities. So concentration. By extrapolating this graph, what will be happen? So what will be happen? So by extrapolating this graph, so we are getting the limiting molar conductivity of the strong electrolyte, but not the weak electrolyte. Even though how much extrapolating the weak electrolyte, we does not get the lambda limiting molar conductivity of the weak electrolyte. So then what will be happen? See this one. Yeah, see this one. Next, Kohlras law and Kohlras law of independent of migration of ions. Okay, what is Kohlras law? What are the applications of the Kohlras law? We will discuss here. See. So what are the applications of the Kohlras law? We will discuss here. What is Kohlras law? So in previous slide, this see. So we are unable to calculate the limiting molar conductivity of the weak electrolytes. To calculate the especially weak electrolyte molar conductivity, so Kohlras law was introduced. What is Kohlras law? It states that limiting molar conductivity of an electrolyte is represented the sum of the individual contributions of the anion and cation. Okay, so here we are taking the lambda naught of sodium plus and lambda naught of Cl minus. This is limiting molar conductivity of the sodium ion. This is limiting molar conductivity of the chlorine ion Cl minus Na plus, or the limiting conductivities of sodium and chloride ion respectively. Then the molar conductivity of the sodium chloride Na lambda naught of NaCl gives lambda naught of Na plus lambda naught of Cl minus. So what is the mathematical equation for the Kohlras law? Lambda naught m equal to V plus lambda naught plus V minus lambda naught of minus. The here lambda naught of plus lambda naught of minus indicates the limiting molar conductivity of corresponding cation and anion, and V plus V minus represents the number of coefficient, how many number of ions are present. For example, we are taking here lambda naught of HCl. So how many number of on ionization HCl gives the H plus ion plus Cl minus. So one ion it will be give on ionization. That's why lambda naught of H plus ion plus lambda naught of Cl minus ion. So what is happening here for the ammonium chloride? This is also lambda naught of NH4 plus lambda naught of Cl minus for water. So in general, this one, if you take by electrolytes, whatever the beryllium chloride, BaCl2, it will be ionized into Ba plus 2 Cl minus. So here lambda naught of barium plus 2 Cl minus ions. So here V minus indicates the 2. That is the coefficient of the number of ions present in that one. Yeah. So limiting molar conductivity of the some ions is given in water at room temperature 298 Kelvin. So here what is the ion? We are taking here cations, all whatever the H plus ion, sodium plus ion, K plus ion, calcium plus ion. So here what is the limiting molar conductivity of H plus ion? 349. Okay, Siemann centimeter square mole inverse. These are the units for the limiting molar conductivity units. So here for the sodium 50 and potassium 73, calcium 113. Here anions also mentioned in this table. So OH minus, Cl minus, Br minus, acetate ion CS3 CO minus mentioned 199, 76, 78, 40. Then see this one. Yeah, by using that one, so by using this table we can calculate the limiting molar conductivity of the calcium chloride and calcium hydroxide. So what is data is given here. From the data we have to calculate the molar conductivity of the calcium chloride as well as calcium hydroxide. So calcium plus ion as well as Cl minus. Calcium chloride will be ionized into how? Calcium 2 plus 2 Cl minus. This is a Kohlras law. Okay. So whatever the calcium plus, it is independent of that migration. Even though it is attached to chloride ion, bromide ion, hydroxide ion, whatever the, it independently gives some value, fixed value. Okay, that is the Kohlras law. Now we have to calculate the molar conductivity of the, what is that one? Limiting molar conductivity of the calcium chloride. So what is the, according to Kohlras law, this one. So lambda naught of calcium plus 2 lambda naught of Cl minus. Simply we have to substitute the lambda naught of calcium plus 2 into Cl minus ions. So lambda naught of calcium plus 2 is how much? See this one. Here 119. We are substituting in this equation simply. 119 plus how much? 2 into here 2. These two coefficient, 2 chloride ions are present. That's why 2 into 76 is the value for the chlorine ion. Here see this one. Here how much? 76 is present for the chlorine atom, chlorine ion, not atom, chlorine ion. So that's why we are substituting the here 76.3. So 119 plus 152. So total 271.6 Siemann centimeter square mole inverse. According to the Kohlras law, we can calculate the, so whatever the molar conductivity, limiting molar conductivity of the calcium chloride. Similarly, you have to calculate the, what is that one? Limiting molar conductivity of the calcium hydroxide by substituting the calcium plus 2 plus here 2 OH minus. What is that one value here? OH minus. You have to substitute the 199. So calcium plus 2, how much? 119 plus 2 into 199. You have to substitute, then you can get the limiting molar conductivity of the calcium hydroxide. Similarly, this is also homework you have to do. Calculate the limiting molar conductivity of the magnesium chloride for the independent. So migration, what is value of the magnesium plus 2? You have to refer the textbook. Okay, so in there magnesium plus 2 value is there, then chlorine, all these values are here. Whatever the chlorine ion is present, So you have to substitute 76 value like that. So you have to calculate limiting molar conductivity of the magnesium chloride, sodium chloride, potassium bromide, and sodium acetate. All these you have to calculate simply by substituting the value. So magnesium chloride will be ionized into magnesium 2 plus 2s 2 Cl minus. Sodium chloride will be Na plus Cl minus. So you have to substitute sodium plus and as well as Cl minus values. Then you can get the corresponding value. Yeah, now see what are the applications of the Kohlras law. So actually three applications of the Kohlras law is there. First application is we can calculate the what is that one limiting molar conductivity of the weak electrolytes. So in this equation, what by extrapolating we can obtain the limiting molar conductivity of the strong electrolyte, but we cannot obtain the limiting molar conductivity of the weak electrolyte. That's why by using the what is that one Kohlras law we can calculate the limiting molar conductivity of the weak electrolyte. So this is the main application of the Kohlras law. So what is that one we are taking here? AB. For example, AB is a weak electrolyte. Then by using the corresponding strong electrolytes, we can calculate the limiting molar conductivity of the weak electrolyte. Here AC, DC, DB. These three are the strong electrolytes. By observing one problem, it is clear for you. And also, second application of the Kohlras law is we can calculate the dissociation constant or association constant Ka. Okay, by using this one. And third application of the Kohlras law is solubility. We can also calculate the solubility. Here solubility S equal to K into 1000 by lambda naught M. We have to substitute here lambda naught. Here we have to substitute lambda naught M. So these all are the limiting molar conductivities. Okay, see this one. So here solubility S equal to specific conductance into 1000 divided by lambda naught M. Here lambda naught M represents the limiting molar conductivity. These three are the applications of what is that one Kohlras law. So in this first we will see the first application calculation of the molar conductivity of the weak electrolytes. So we have to calculate the weak electrolyte. What is that one? Acetic acid. It is a weak acid, so it is considered as a weak electrolyte. All weak acids as well as weak bases are weak electrolytes. So now we have to calculate the limiting molar conductivity of the acetic acid. For that, we have to take corresponding strong electrolytes. What is the strong electrolytes? So lambda naught of acetic acid equal to HCl plus sodium acetate and NaCl. So we are adding here HCl plus sodium acetate minus NaCl. Then how it will be ionized? Lambda naught of MH plus lambda naught of Cl minus. Here lambda naught of acetate ion CH3COO minus plus lambda naught of Na plus. All these are positive signs, and here minus of lambda naught of Na plus minus of lambda naught of Cl minus. Here positive Na plus, negative Na plus. Here negative Cl minus, here positive Cl minus. So both four ions are get cancelled. NaCl it will is there negative sign, here NaCl positive sign is there. So four ions will be get cancelled. Then what are the remaining? Lambda naught of H plus lambda naught of CS3COO minus is there. Then by substituting these three values, so what is the value of given for the HCl? Lambda naught of HCl 426 Siemens centimeter square mole inverse. These are the units. So 426 value is given. Next, we have to substitute these three values in this equation. 426 correspond to the HCl and sodium acetate correspond. How much value is given here? 91. And minus of NaCl is given 126. So by substituting these three values, we can get the acetic acid 391 Siemens centimeter square mole inverse. This is the limiting molar conductivity of the weak electrolyte. That is, we are taking here acetic acid is a weak electrolyte. Okay, this is one of the major application of the Kohlras law. Then what is electrolytic cell and electrolysis process? Okay, see, first class we have discussed about the what is the interconversion between the electrochemical energy and chemical energy. So it is electrolytic cell. Okay, so in this cell what is happening? The conversion of the electrical energy to chemical energy. Okay, yeah, so where in electrolytic cells, that means by supplying the some electricity, some chemical reactions will be takes place in the electrolysis. Yeah. So best example for the electrolysis is this one. So by electrolyzing, what we are taking here, so one electrolysis is this one. So in this we are taking one of the cathode, this one, this is anode. Okay, by connecting to the battery. So what is happening here, we are taking as a pure copper as a cathode, and here impure copper as a, sorry, impure copper as a anode. By corresponding solution we are taking here copper sulfate solution. Then what will be happen, by connected to the battery, so electrolysis process will be happened in this. So what will be happen at cathode, so here see this one, at cathode what reaction will be happen, reduction will be takes place. So copper 2 plus ion plus 2 electrons gives copper. That means at the cathode copper is depositing. Next, at the anode what the reaction is happening, oxidation. At anode oxidation will be takes place, at the cathode reduction will be takes place. Here at the anode copper gives copper 2 plus 2 electrons. That means here oxidation is taking place. So by using this one, this picture, it is very clear. So here first of all we are taking pure copper as a cathode, here impure cathode as a anode. So what is happening, by passing the electricity, so impure copper, so these are the impurities, then pure copper is depositing on the pure, this one, this electrode, on the cathode electrode. So that means impure copper is dissolving in the copper sulfate solution, and that means it is undergoing oxidation and it is undergoing reduction. That is impure copper, whatever the pure copper is depositing on the cathode. Okay, this is the overall reaction. So what is the application of the electrolysis, we can prepare the pure compounds, whatever the metals, especially sodium, copper, magnesium, these can be prepared by using the electrolysis process. Okay, so from the impure metals to pure metals we can convert by using the electrolysis process. Next, what are the quantitative aspect of the electrolysis? Two aspects are there. So Faraday is one of the scientists, he proposed two rules. Okay, so first he proposed two laws. First law is Faraday's first law. So what tells the Faraday's law, first law? According to the Faraday first law, mass of the substance, okay, is directly proportional to quantity of the electricity passed through a electrolytic solution. That means his directly relation is there. What way, from mass of the substance and quantity of the electricity is passed. So this is a direct relation between the, so mass of the substance and quantity of electricity is passed through a electrolytic solution. So it is explained by the Faraday. That's why it is called as Faraday first law. Okay, M is directly proportional to Q. So where M is the mass of the substance and Q is the quantity of this electricity passed through an electrolytic solution. This is quantity of the electricity. This is the mass of the substance, whether it is dissolved or liberated, what is whatever the, okay, deposited through the what is that one. So M by taking the proportionality constant, M is directly proportional to Q, M equal to ZQ. We can also, here Q is in the coulombs. Okay, 1 coulomb equal to 1 ampere into 1 second. Okay, by substituting Q equal to IT, here I is the electricity in the ampere and T is the, so time in second. Okay, so we can take Q equal to IT. So that's why M equal to Z into IT. Here Z is a proportionality constant. So, okay, so what is the Z value? What is the Z? Electrochemical equivalent. So Z equal to E by F we can take. So, okay, Z equal to, Z is a electrochemical equivalent and Z equal to E by F. What is E? Equivalent weight. And what is F? F is a Faraday. So that's why what are the units for the Z? Here equivalent weight will be measured in the kg and Faraday will be coulombs. So that's why kg for coulomb. This is the unit for the Z. So final reaction equal to M equal to ZIT. This is the mathematical representation of the Faraday first law. So then one numerical problem based on this one. So what is that one? This is the picture indicates the Faraday's first law. So simply, what is Faraday's first law? M is directly proportional to Q. That is the Faraday first law. So one of the numerical problem based on the Faraday's first law. So here A or I both are same. Okay. A or I current in the ampere, T time in second, Z is a, what is that one? Electrochemical equivalent. These three values are given in the question. Actually, question I am not given directly. Z is given, A is given, T is given. So A and I both are same. That is current in ampere. T is time in second. Z is electrochemical equivalent. These three values are given. Then what is question is given? Find out the amount of mass of the substance deposited. So W equal to Z into A into T, or W equal to Z into I into T. So by substituting these three value, 3.2 into 10 power minus 7, this is belongs to the Z value, and A equal to zero point 0.5 ampere, and T equal to here 60 minutes. That's why 3600 seconds. By substituting these three, what will we get? 5.9 into 10 power minus 4 kg. This much of, so weight of the substance deposited. Okay, yeah. So this is a formula, one of the mathematical equation belongs to the first law of Faraday's law. And what is the one more problem belongs to the Faraday's first law. So what is the problem is given? A solution of copper sulfate is electrolyzed for 10 minutes with a current of 1.5 ampere. That means here time is mentioned, as well as what are the, how much of amount of electricity is passed mentioned. Then what he is asking? Mass of the copper. Simply, so how much of mass of the copper is deposited at the cathode? He is asking that one. So simple. So Q equal to IT. So we are calculating Q. Q equal to IT means we are taking here I in the amperes. So 1.5 ampere is given, and 600, 10 minutes equal to 600. 10 into 60 equal to 600 seconds. So 900 coulombs of the electricity is came. Okay, Q equal to IT. Yeah. So what is the chemical reaction happen at the cathode? Copper 2 plus 2 electrons. Here by accepting 2 electrons, copper 2 plus is converting into copper. We require 2 Faradays. Okay, yeah. So by to deposit the copper, 2 electrons are required. That means 2 Faraday of electricity is required. So, okay. So we require 2 Faraday means 2 into 96,487 coulombs. 1 Faraday equal to this value. So to deposit 1 mole of this copper substance. How much? 1 mole means mole equal to weight by gram molecular weight. So here 63 is the molar mass. That's why 63 grams to deposit 63 grams or 1 mole of the copper. How much of amount of energy is required? That means electricity is required. 2 Faradays are required. But here how much? How many coulombs are there? Only 90 coulombs are there. Okay. 2 Faradays is equal to 63 grams. Then 96, sorry, 900 coulombs equal to how much of it? Simply by cross multiplication. That means 2 into 96,500 is 63 grams. Then 900 coulombs equal to how many? X. By cross multiplication, we can get 63 into 900 divided by 2 into 2 Faraday. So 0.29 grams will become. Okay, that is according to the first law. What is second law? Second law, Faraday's law. So second law indicates this one. When same quantity of electricity is passed through a electrolytic solution, where the electrolytes have different electrolytic solution, so the mass of the substance is deposited according to their chemical equivalent. Okay. So when these three electrolytes are connected in this series, what is happening here? Same quantity of electricity is passing. Then what will be happen? The mass of the substance deposited according to their equivalent weight. Okay, here E indicates the equivalent weight. Here we are taking sulfuric acid and copper sulfate and silver nitrate. These three are the different types of electrolytes solutions. Then equal amount of the solution, whatever the electricity is passing these three. So here equivalent of HCl, whatever HCl or H2SO4 equal to 1. Copper sulfate, so equivalent weight 63 divided by 2. 2 electrons will be required to copper 2 plus 2 copper. That's why. So 31.75. And silver nitrate, only 1 electron is required. So Ag gives Ag plus 1 plus electron, or Ag plus electron gives Ag. So that's why what is the atomic weight of the silver? 108. Here 1, here 31.75, here 108, like that. So what is the mathematical equation for the second law of the Faraday? W1 by E1 equal to W2 by E2. We can also take ZIT, W equal to, from the first Faraday's law. So by equating these two, we can calculate the equivalent weight. Okay, this is the interrelationship between the So Z and E. So one of the mathematical problem regarding this Faraday's second law. So what is a current of 1 ampere is passed through a solution of copper sulfate and silver nitrate connected in the series. Okay, 1 ampere of current is passing through the copper sulfate as well as silver nitrate solutions. So what is happening? 0.6635 gram of the copper is depositing. Then calculate the silver. Okay, simply W1 by E1 equal to W2 by E2. W1 double of copper by double of silver equal to E of copper by E of silver. What are the values are given? Weight of the copper is given, equivalent of silver is given, equivalent weight of copper. We know that these two values. Simply we have to calculate the weight of the silver. Weight of the silver equal to 0.6035. So this weight is given and equivalent weight of silver. How much? 108 divided by 31.75. So final weight of the silver equal to 2.16 grams. Okay, this is the interconversion between the whatever the equivalent weight and weight here. W1 by E1 equal to W2 by E2. So from this we have completed the electrochemistry chapter. So today's class, what we have discussed, please see once again from this one. So we have discussed the Kohlras law and its application, Faraday's law. So this is Kohlras law. What is the changes will be happened? So with the dilution, so conductivity and molar conductivity changes with the dilution. See with this one. So we cannot calculate the what is that one? Limiting molar conductivity of the weak electrolytes. That's why Kohlras law was invented. So this is the Kohlras law, independent of the migration of the ions. So this is a Kohlras law. Next, what will be happen? So this is one of the application of the Kohlras law. What we can calculate the molar conductivity of what is that one? Weak electrolytes by using the strong electrolytes, corresponding strong electrolytes. Next one, what is the topic? Electrolytic cells. What is the electrolysis process? What is the electrolyte? So major application of the electrolysis, electrolytic cells or electrolysis is we can prepare the pure metals from the impure metals. One of the example is this one. Copper is prepared from the impure copper sulfate solution. This is impure copper. This is copper. So first we are taking like this. So this is converting impure to pure like this. So extra pure copper is depositing on the cathode here. So cathode cation reduction takes place. Anode anion oxidation will be takes place. Okay. So sodium, magnesium metals as well as copper, some of the metals can be prepared by using this method. And quantitative aspect of electrolysis is two laws. What is that one? First law of Faraday and second law of Faraday. So M is directly proportional to Q. This is the first law of the Faraday. So this is a picture indicates the Faraday's first law. So this is the one of the numerical regarding the Faraday's first law. Simply we are calculating the weight of the substance depositing. Okay, here same we are also calculating the weight of the substance, but here by using the Faraday's we are calculating. And second law of the Faraday, here it depends upon the equivalent weight. So that is the major difference between the Faraday first law and second law. Okay, in first law it depends upon the weight of the substance. Here equivalent weight of the substance. Okay, yeah, see this one. This is a one more problem regarding the second law of Faraday. So from this electrochemistry has completed. So next session we will discuss about the chemical kinetics. Okay, yeah, so some more is there any problem is there? Just you have to focus on the what is that one. Please see once this one. So what are the objectives are there? You have to see this one. Yeah, you have to focus on what we have discussed in entire electrochemistry types of cell. Two types: electrochemical, electrolytic cell, and cell EMF, nearest equivalent. This is important. So numerical problem also will become. So the relation between the concentration and temperature and E cell value is there. E cell equal to E naught cell minus RT by NF ln K equilibrium. That is nearest equation important. And numericals also come from this one. What is that one? So what is conductance, resistance, molar conductance, equivalent conductance, like this, those also important. And the nearest and also what is that one? Faraday's law. And one more is there, Kohlras law. Okay, so all these topics comes under the electrochemistry. So next class we will discuss about the what is that one, chemical kinetics chapter. Okay, I hope it is clear. Okay, thank you one and all.